as the first keynote speaker of the conference this year, Kathleen Fisher. And Kathleen is an ACM fellow and a past chair of ACM SIGPlan. And many of you will know her from her long history in functional programming, including work on the Moby programming language and the PAX family of systems for processing ad hoc data. And also because she was chair of both ICFP and CFP in the past. Kathleen used to work at AT&T Labs and is now a professor at Tufts University. And for the last 2 years, she was on leave from that to be a program manager for DARPA, where she led the HACMS and HAMO, if I pronounce that correctly, programs. And today she will tell us all about the great work behind one of these acronyms. So thank you, Kathleen.
Thank you. Thank you very much for that introduction, and the microphone is indeed working. Right, so I am here today to tell you about DARPA's HACMS program. So what is DARPA in the first place? DARPA is a funding agency in the Department of Defense of the US government that is focused on creating and detecting strategic surprise. It's a bottom-up organization where programs are created by program managers who rotate through. Basically, all program managers at DARPA are there on fixed-term appointments for short periods of time. I think the thought process being that any one individual is only good for a certain amount of surprise, so DARPA takes you a few years, sucks the surprise out of you, and then kicks you out so that they can get new people in to get new strategic surprise. I think it's also why it's a bottom-up organization, because if you have a top-down organization, it's only good for the surprise that the people at the top can think of, whereas when you're bringing in people at the leaves and they're the ones responsible, then you get a lot more surprise covered. So HACMS is a 4.5-year program. That's the typical length of a DARPA program. And typical terms for academics are kind of like 3 years. So I finished my term, I rotated out, and HACMS is now under new management. But I was happy to leave partly because John Lunchbury is taking over management of HACMS. So I was confident that the program would still be under good terms. I think John is probably here somewhere. So he can answer questions about where HACMS is going in the future if you're curious later. So what is HACMS? HACMS is focused on using clean slate, formal methods-based approaches to making embedded systems that are provably invulnerable to certain classes of attacks. So what does that mean? So we've worried for a long time about cybersecurity of things that look like computers, but it turns out many, many objects, sort of everyday normal-looking objects, are in fact these days computers, networked computers, and that we need to worry about the cybersecurity of these kinds of devices as well. Everything from SCADA systems that control large industrial infrastructure like the power grid or sewage treatment plants, to medical devices like pacemakers and insulin pumps, to computer peripherals like printers and scanners and routers, to communication devices, to vehicles, and even everyday household objects like televisions and refrigerators these days are actually network processors. It turns out that hackers and or researchers have shown that each of these systems have vulnerabilities that can be remotely exploited. For example, there was a hacker in Australia broke in wirelessly to the Maroochydore sewage plant and caused raw sewage to dump into a park area. Or Jerome Radcliffe at Black Hat a couple of years ago showed that he could wirelessly hack into his insulin pump and cause it to deliver incorrect dosages of the medication. Saul Staffo at Columbia showed how he could wirelessly hack into printers and laser printers and cause them to catch on fire, or to Cisco telephones and exfiltrate information. Researchers at the University of Washington, the University of California, San Diego showed that they could hack into cars, and recent reports have talked about refrigerators being on botnets. There's some question about that last report, but it's probably just a question of time. So just diving in a little bit into the automobile space, this is work that Stefan Savage at the University of California, San Diego, and Yoshi Kano at the University of Washington did a couple of years ago. In the first paper, let me step back a little bit and tell you a little bit about a modern automobile. You might think that a car is just a car, but in fact, it's really a computer on wheels. A modern automobile has somewhere between 30 and 100 embedded control units, or ECUs, that are all computers of some size, and they're networked together via a number of different communication buses, often CAN buses. Some of those buses are high speed, some of them are low speed, And people sometimes think that high speed means high security and low speed means low security, but in fact that's not at all true. They are just different speeds, and what the work that Yoshi and Stefan did was they showed that if they could connect to that network, then they could rewrite, reflash all of the software in the car and take over control over anything on the car that is controlled by software. And in fact, getting access to that network is not all that difficult because cars are required by law to have diagnostic ports that allow mechanics to plug in and read out diagnostic information to perform software updates. So what's under software control in a typical car? Well, pretty much everything, right? Anti-lock brakes mean that braking is under control of software. Cruise control means that acceleration is under control of software. The little key fobs that let you unlock the car doors remotely means that the locking is under software control. The fact that the entertainment system does the little beeps in the car, all of that is under software control. Right, and there are lots of really good reasons why all of those things are under software control, for all the reasons why you want things to be under software control in general. So the fact that basically everything in your car is under software control is a good thing in general and is not going to go away. So we need to figure out how to make it so that you can't reflash them, anybody can't reflash them. So the reaction to that first paper showing that they could, if they could connect anywhere to the network in the car, they could rewrite all the software in the car, was a little bit muted, since the way they connected to those networks was they plugged into the diagnostic port under the steering wheel. And if you were plugged into the diagnostic port under the steering wheel, well then you were in the car. You already had physical control of all those things, so what's the big deal anyway? They then showed in a second paper that they could achieve the same effect, the exact same effect of rewriting any of the code in the car remotely without touching the car in 4 different ways. They showed that they could place a virus on the computers in the repair shop, and then when the mechanic connected it to the CAN bus, they could spread the virus to the car that way and take over control. They showed that they could break in through the Bluetooth interface. They showed that they could break in through the telematics unit. So the telematics unit is the thing like OnStar or InSync. Each different manufacturer calls it a different thing. It's a very useful feature. It means if you get in an accident, the car will call the equivalent of 911 and arrange for help to come to you. It arranges for them they can automatically unlock the car for you if you lock yourself out. But it also means that your car has a cell phone number, and that what they found was that they could basically repeatedly call that cell phone number and eventually break the authentication and be able to break into the car. The expected time to do that was about 12 hours. But there's no indication in your car that anybody's calling your car, and so they have 12 hours if they need it, basically. The last attack vector was through the infotainment system in the car. They basically created an electronic version of a song that played fine in their home stereo systems or on their computer, but when they put that particular song on a CD and played it in the car, it caused a buffer overflow in the software in that particular car and allowed them to take over control of the car. Right. So the reaction to this was a little bit less muted. The car industries have really ramped up their efforts to try to increase security, but it's not clear they have the right expertise yet to do that. Okay, so what are we going to do about this? How are cyber-physical systems supposed to be secured? Well, people have had a security defense for a long time. The mechanism has been twofold. One has been air gaps, and the other has been obscurity. So air gaps was cyber-physical systems used to not be connected to anything. But that is pretty much completely no longer the case for a lot of really good reasons, right? It's not for bad reasons that cars are now connected to networks, right? You want to have the telematics unit, you want to have a stereo system, you want to have a Bluetooth interface. So lots of good things that functionality is adding, but it means that the car is networked and therefore needs to be treated as a network system for security reasons. It turns out it's not just cars, but all sorts of cyber-physical systems are now networked for things like being able to upgrade functionality, for being able to remotely monitor what's going on, for being able to provide new functionality. So the network connections are really not going to go away. Really, to a first approximation, all computer systems these days are networked. Even supposedly high security systems end up being networked, not constantly, but intermittently when they're connected to do software updates and things like that. Taking a USB drive from one system to another is in a way providing network connectivity over time. The second defense has been obscurity, right? Nobody knows these systems. But it turns out that's actually not true anymore either. Tons and tons of documentation is available on the web. You can search for the names of systems, the names of processors, and get documentation. Often the documentation includes the passwords, so the passwords are hard-coded in and not easy to change. It's also the case that you can buy examples of systems. You can go online and say, oh, I want this particular kind of part, and so you can bring it in and bring it into your lab and be able to reverse engineer it. Also, we as a computer scientists have built tons and tons of tools for being able to analyze software, and that those tools for analyzing software are very useful for analyzing software for embedded systems that can be used then to reverse engineer them. And embedded system code tends to be smaller, so it tends to be like easy cases for our our analysis tools as opposed to the harder cases. So basically, they're no longer air-gapped, and they're really not very obscure, so relatively easy to break the old means of defense. So the next approach was like, okay, well, let's take traditional approaches to security for desktop systems and apply them to the embedded system space. Well, that doesn't work very well either for a couple of reasons. The first of which is that approach doesn't work very well even on desktop systems. So when you apply it to embedded system space, it doesn't help very much, right? The standard approaches of intrusion detection, antivirus monitoring, those are looking for known vulnerabilities, so they're not really any good against new vulnerabilities. The other thing is that those are itself, like antivirus scanning, intrusion detection systems are complex pieces of software, millions of lines of code that themselves contain vulnerabilities. So for example, the chart here that you probably can't read shows the October 2010 vulnerability watch list. There were 17 things on the list, and the ones that are marked in red are security vulnerabilities that were themselves in security code. Right? So the security code was introducing new security vulnerabilities. That doesn't mean that you shouldn't have been running the security prevention code. It was shifting the vulnerability from one place to another place, giving the defenders time to fix the new vulnerabilities, so you're kind of in this constant arms race. But it does mean that the approach is kind of fundamentally not going to get you a system that's secure in the end. Also, this whole approach on desktops relies on the fact that the desktop has tons of resources available. Right? Like, I used to joke that my DARPA laptop had 2 processors, one of which spent full time monitoring to see if the system had been attacked. And that was fine, because we didn't really know what to do with the second processor in the desktop laptop, in the sort of laptop, except do the monitoring. But in the embedded system space, that's completely not the case. Right? Processors are sized exactly for the expected workload of that particular device. They don't have the capacity to do twice as much work just monitoring to see if anything happened to go wrong. So that also is going to be a problem in the embedded system space. Often code in embedded systems is highly regulated. It has to go through a complex review process before it can be pushed out into the world. And so you can't have a sort of Patch Tuesday infrastructure where every Tuesday you push a new feature, because there has to be a months-long process to get the code approved. So for these reasons, kind of traditional approaches to security on desktop systems are really not applicable to the kind of embedded systems that we're talking about in vehicles. So we really need a fundamentally different approach. So what is that going to be? So this is my attempt to explain to DARPA that I think we should use a formal methods-based approach to producing high security. So producing code that provably doesn't have many of the kinds of vulnerabilities that hackers currently like to exploit to be able to break into systems. That doesn't mean that there aren't other threats that this will not address, but it addresses a large class of currently relevant attacks. And why do we think that formal methods-based approaches might be successful? They've certainly been tried for a long time. Why now, in some sense? And this slide is showing the sort of answer to the why now question. There are really kind of 2 answers to that. One is that the formal methods community has produced a set of tools, an infrastructure that's now ready, in some sense, to be applied to these kinds of systems. Things like model checkers and theorem provers, the existence of Isabelle and Coq, that are developed to a mature state where they can be used on these kinds of problems. And the second, the sort of driving function behind why a lot of these tools are now more automatic and can be used, not easily, but within the scope of what's possible, is because of the amazing advances in SAT solvers in the past 10 years. So this graph shows the compiled results of the SAT solver competition every year. Daniel Lebert took the winning system for the past 10 years in this competition and ported them all to one machine and ran all of them on the 2009 problems and plotted them out. So each line there corresponds to one solver, and the horizontal axis is the number of problems solved, and the vertical axis is how much time it took to solve them. So you can just pick one point in this spectrum, which is the 80 problem point. So how long did it take to solve 80 problems? And the best time improved from 1,000 seconds in 2002 to only 40 seconds in 2010. So that's 2 orders of magnitude improvement on top of the improvement that's seen in hardware, just because the computers themselves got faster. So in some sense, like this was the money slide really going to DARPA saying, you know, why should we do this now? It's like, look at these amazing improvements. Let's see what these amazing improvements could do in terms of the formal methods-based techniques. So what are the techniques that I'm talking about? There are really kind of three different approaches to formal methods-based systems that we're exploring in the HACMS program. The first is code synthesis, where instead of having a person write code, and somehow people seem to be unable to write C code that doesn't have buffer overflow kinds of attacks in it. Could we get it so that computers could write that code instead and write it in a way where the computer produces, in addition to the code, also a proof that the code is memory safe, for example. The second approach is using domain-specific languages, and the third approach is writing code within the context of a theorem prover and producing both the code then and a proof that the code is correct. This is the mechanism that Xavier used in the ComSort compiler. It's the approach that the NICTA SEL4 team used in producing the SEL4 verified microkernel. And here the research is in automation. How can you increase the level of automation in producing these kinds of proofs and systems? Okay, so what is the, I went through that much faster than I usually do. So this is the structure of the HACMS program. The way DARPA works is the person who comes up with the program creates called a broad agency announcement that describes the structure of the program. And there are different kinds of tasks in the program that are called technical areas. Each technical area is focused on a different technical problem. And collectively, the whole group of performers are responsible for solving a particular kind of problem. So performer is DARPA's word for people working on a DARPA contract. It includes academics, it includes people working in research labs, people working in companies. Basically, DARPA can give money to anyone who is the most qualified to be able to accomplish a particular task. Unlike, say, the NSF in the US, where you have to give money to people at US institutions, DARPA, anybody who is the best qualified to do a particular task is fair game. So the BAA describes the different roles, and then people submit bids to say, I want to do this particular piece. So HACMS had 5 technical areas. Each column here represents one of those technical areas. The first technical area are the vehicle experts. So these are people in industry who have real problems with security of vehicles, and their role in the program is to represent those sort of practical real-world problems to the rest of the people working on HACMS, and then to take the solutions of the rest of the people working on HACMS and apply them to their vehicles that they're experts in. Technical area 2 is the operating system group. The teams in this column are focused on kind of infrastructure, low-level operating system kinds of tasks. Technical area 3 are control systems. These are groups working on producing sort of the flight control or cruise control, or the kind of control system theory kind of tasks. Technical area 4 is working on research integration. So this technical area actually has 3 different subcomponents. One of those is actually managing the rest of the performers to produce a working version of the systems. Then the second part is working on composition. So one of the really difficult technical challenges in this area is how do you take high assurance components and put them together to get a high assurance system, right? A lot of the properties, security properties, and other properties you care about whole systems are not compositional. You can't just sort of break it up into smaller instances of the same problem and then put them together in a natural way. You have to be very careful about how you do the composition. And so that's a research challenge of technical area 4. And then the third part of the challenges for technical area 4 is the tool infrastructure to do that. Can you build a system that integrates all of the pieces of the other technical areas and put them together to give a sort of system-wide assurance property? Then the last area, technical area 5, is the red team. So one of the really very difficult challenges of the whole security space is how can you tell how secure a system is? Right? I think, in fact, nobody has any kind of a good answer to this problem. Right? You have to like any kind of security assessment has to be done with respect to a particular threat model. And how do you come up with that threat model? How do you know that you've captured all of the important aspects of a threat model for your system? And then how do you measure? Like once you actually have a threat model, it can be more of a principled process of figuring out how secure a particular system is with respect to a particular threat model. At the moment, as a result of this imprecision, the state of the art in assessing the security of a system is you hire a red team, which is a team of, in some sense, white hat hackers, people who try to break into systems for a living, and then you measure kind of how much effort did it take this team to be able to break into the system. This is clearly imperfect since it relies on, well, how good is the red team? But it's the state of the art and how you measure this kind of thing. So so that's the sort of vertical columns. The horizontal column, or the top row, is the air team. So this group bid, in fact, as an entire team. They put together a single proposal that had all of these pieces. The vehicle expert is Boeing. They contributed access to what's called the unmanned Little Bird, which is a helicopter based on the Apache airframe that can fly autonomously, or it can have a pilot. So it's a pilotable unmanned Little Bird. And the advantages of that is that it's a lot easier to arrange for flights, test flights, if you can have a pilot in the vehicle that can take over control if necessary. So the air team is working on producing a high assurance version of the Boeing unmanned Little Bird. They're also working on, each of the teams, in fact, has a second open source version of the vehicle. In this case, they call it the Spacocopter, which is a unmanned Little Bird, is a open source hobbyist UAV that's about this big, that they have full access to all the source code, so that they can see everything, they can change all the software, whereas the unmanned Little Bird, the software is proprietary to Boeing, and so the full research team can't have access to all of the code. NICTA is providing the operating system pieces, so we're building on the SEL4 verified microkernel, which is one of the motivations for doing the project in the first place. Galwa is doing the flight control system, and Rockwell Collins with the University of Minnesota is working on the integration and the tooling infrastructure. The rest of the green pieces here are the ground team. They're working on an American-built car. So one of the things that's important to note is that we don't think that any one particular car is more vulnerable than lots of other cars. So like the work that I told you about from the University of Washington, the University of California, San Diego, they were very careful to not publicly disclose what car it was that they were able to hack into, since pretty much everybody's understanding is that all cars are essentially equally vulnerable to these attacks. So there's no reason to think that any one particular car is more vulnerable than any others. And so in the program, we're very careful to always call it an American-built car, as opposed to saying what car it is exactly that we're working on. And that's why we have this really hideously ugly picture of a car as the car. Right, so that's the car they're working on. And then they also have an open source vehicle. In this case, it's called a Land Shark, which is an unmanned ground vehicle. It's a robot that's about this tall and this big across, that they have full access to the source code. Right, and then the red team is led by Draper with AIS in Rome and University of Oxford as a sub, and they're working on normal penetration testing, plus they're working on using formal methods-based approaches to do penetration testing, using formal methods to do that. So for most of the rest of the talk, I'm going to talk about the air team. At the very end, I'll go back and just say a few things about what the ground team is doing. There's no reason to, basically both teams are making really good progress, and it's easier to just tell one story with the air team, but I'd be happy to talk to you about the ground team if you have questions about that too. Okay, so then at the very beginning of the program, we had the red team conduct penetration testing exercises against all four of those vehicles, the two open source vehicles and the two commercial vehicles, and see what they could find. Basically, they were able to break in and take over control over all four of the systems. They didn't actually fully take over control of the car, but they could have if they had more time, basically. And all of the rest, they had really no trouble whatsoever connecting in and taking over. And part of that is because the systems have been engineered to be easy to connect to. So it's not like the manufacturers would be at all surprised that this is the case. It's they've wanted to make sure that the systems were always was always able to talk to the other system, and so the fact that you can talk to them is not a surprise. So this shows a little demo of the breaking into the quadcopter. The person speaking here is the lead of the Rockwell Collins.
This is an AR drone quadcopter. We'll be using its airframe in our research vehicle in the HACMS project. Eventually, we'll upgrade its control electronics so that we can host the provably secure software that we're developing on the project. But for now, it serves as a convenient platform to demonstrate the kind of security vulnerabilities we're concerned about in HACMS. Even though it is essentially a toy, it illustrates the same sort of vulnerabilities that can be found in many network-enabled cyber-physical systems, including automobiles, SCADA systems, and aircraft. The AR drone is controlled using standard Wi-Fi technology. It acts as a Wi-Fi access point to which you can connect with a phone, tablet, or PC running the ground station application. AirCrack is a readily available software package for monitoring and injecting traffic onto wireless networks. We will use it to attack the AR drone from this laptop. First, we identify the physical address of the drone access point. Next, we send commands to de-authenticate all clients, including the ground station. The ground station now has no control over the vehicle. The attacker laptop has taken control of the vehicle, and the ground station is not able to reconnect. Finally, we can send arbitrary commands from the attacker laptop. In this case, we will simply cause the vehicle to land. Even though this was a very straightforward attack, it is representative of some of the current threats to network cyber-physical systems that we will address in the HACMS project.
Right, so hopefully that gave you a sense of kind of viscerally how easy it is to break in and take over control, and also how frustrating it is to be the person who's supposed to be able to control the device and in fact have that control wrested from you by somebody else, but unexpectedly. Right, so in fact, in the University of Washington work, when the people were in the car, the student who was the driver who was in the car on a closed raceway when they were demonstrating being able to remotely break in and take control, right? He had to sign a death waiver saying that he was willing to be in this car while it was remotely hacked into, and then it was really freaky when driving the car and all of a sudden like the brakes stopped working. It's like he had a walkie-talkie. It's like okay, you can put the brakes back on again. Right. In fact, 2 weeks ago, I had the opportunity to be in that same position where I was in the car when the University of Washington researcher was playing the role of hackers, broke in and took over control of the car while it was being driven. It was even though I knew it was going to happen, it was very surprising to be in the car and all of a sudden to have the driver like pushing on the brakes and nothing happening, or conversely, not expecting the brakes to be on, all of a sudden slamming in the brakes. Or I was in the driver's seat and the seatbelt just all of a sudden sort of like how it has the tensioner on it where it can be various degrees of difficulty, right? So that the hacker basically broke in and made it slam you back into the seat and basically hold you restrained against the seat. It was very freaky. Okay, so. That's the beginning of the program, right? The red team was able to break in and take over control. So what is the air team doing in response to that threat? So this slide sort of tries to summarize what they did in the first 18 months of the program, so the first phase. The way the program is structured, every 18 months, the red team gets to get access again to the current state of the vehicle and try to break in. And of course, that actually means that the red team has to report out at the 18-month period as to how secure they found the system to be. So that means, in fact, the team has to deliver at 16 months instead of 18 months. So what's going on here is the horizontal axis is time. So each of the columns is at a particular number of months. So the left hand is at 0, 6, 12, and 16 months. The bottom shows kind of a schematic architecture of the system, and the top lines show the various teams and what they're contributing to the system. So we started out with the Arducopter that you saw a picture of in the video. It had monolithic software, had no runtime operating system, and had no security really whatsoever. Then the team started by breaking apart the architecture a little bit. They replaced the hardware, so it has slightly more powerful processors, so that there was space to run some more powerful code. The original software assumed it was written for the particular Arduino chip. So they introduced a hardware abstraction layer, and they fit in a free RTOS in between the two of those, so there were abstractions that they could rely on. The free RTOS was available already, whereas the RTOS that they're working towards being able to use from NICTA was in development at the time. So this allowed them to have the copter flying at the 6-month period, even though the NICTA's RTOS wasn't available yet. And then they refactored the monolithic software to pull out this hardware abstraction layer, and the rest of the software stayed in this top box. The the hardware abstraction layer they made available to the Arducopter community. So basically all of the work that's being done in HACMS, except that which is proprietary to the Boeing Unmanned Little Bird or to the American-built car, is open source and released to the broader community. So everything that the air team has been doing on the Arducopter has been released back into the Arducopter open source community and is available from this Copter webpage. So in fact, the hardware abstraction layer was a big hit with that community. Then the next step at the 12-month period was they started to be able to switch out the free RTOS for the NICTA's eChronos